Okay, hello everybody. Welcome to the second video in this attempted series, we'll call it, for reviewing the Biochem 440 lecture slides for fall 2025. Uh, for any mistakes I made on the past video, I do want to mention this. I put some comments in the description of the last video about things that you should be aware of that I may have made a mistake on, or like maybe there's some elaboration that I forgot to mention. I'll keep doing that for the next videos, so just be aware of that and make sure you're checking the comments or checking the description when you see an error. And if there are other errors, please yell at me. But yeah, other than that, my contact information and all that is still on that first video. But yeah, today we're gonna go over the stuff you guys learned about pH dependency, buffers, blood buffering with the bicarb system, and then a little bit of chemistry, right? That you kind of need to know this for this whole thing to make sense. So yeah, let's go ahead and get started. So use your, I guess, use your resources. This is a separate thing, but like use the IC, use Clue, use whatever. But yeah. So this first slide is just showing why do we care about pH. pH is a really important tool. It's useful for a lot of proteins are pH dependent, and that makes it like a really big deal. Also, when we do experimental design, it's important to control for pH. Sometimes you can extract proteins with certain pHs based off of the charge in anion and cation exchange columns, which you guys will be learning about pretty soon, if I'm not mistaken. So they're just useful. A pH is just useful in general. Buffers, obviously, like we're going to talk about, right? Blood buffering in general allows you to make really small changes in pH without completely destroying the system that you're trying to study. So, yeah. All they're trying to show on this slide here is how protein structure is very different depending on the pH we're at. So, like for this protein here, gamma tubulin, right? You can see that if it's at pH 6.8. Sorry, I'm a bit sick as well, if you haven't noticed already. Even the past video I was a bit sick. But anyways, yeah, as you can see here, you can see at pH 6.8, the gamma tubulin clumps up, and then at pH 7.2, more, this is like blood pH right here, it's more in this like linear fashion, right? Same thing here, right? You can see how the change, there's a change from pH 5 to 7, right? You get, oh gosh, from pH 5 to 7, you get like a linearization. From pH 7 to 5, you get more of a like these singular parts. And yeah, so like we said before, biochemical processes are tuned to have maximal activity at a pH of where they are active. So certain enzymes are better at certain pHs, right? So an example of this is like pepsin or enteropeptidase. These are both stomach enzymes, right? And your stomach has a notoriously low pH of 2 or around 1 or 2 due to the HCl, the hydrochloric acid that's released in there. So, yep. And yeah, so the pH must be maintained near its optimum for functioning, right? And so you can see here's some examples. Bones are basic, right? Cytoplasm pH 7. Lysosomes need to be acidic to break down things, and then gastric juices. This is the stomach, right? Gastric is stomach, right? pH 5 is 1.5. And here's some examples, right? You can see these are activity curves, right here. So you can see here that these certain enzymes, alkaline phosphatase is good at around like what pH 8.5-ish maybe. The trypsin is better at around 6.5-ish, 7-ish. And then pepsin, like we talked about, is around 1.52, right? So if we look at concepts related to pH, strong versus weak acids. So you should know like what a strong acid versus a weak acid is, right? The lower, if you think about pKa, right? If you remember what pKa is, right? pKa is like the pKa of any given substance is the point at which it is 50% protonated and deprotonated, right? And so the lower the pKa is, the more acidic the thing is, right? The other thing you have is the pKb, right? Which is the opposite of the pKa, right? It's like the basicity, right? So the lower the pKb is, the higher the basicity is. But then remember that pKa plus pKb equals 14. So if you were given one, you can solve for the other one, right? That's one thing to keep in mind, right? So make sure you remember that. For strong acids and weak acids, again, examples: hydrochloric acid. Weak acids are like acetic acid, carboxylic acids, all these things that you guys learned in OChem. So, and most of the time when we make buffers, or actually, sorry, every time we make buffers, we're going to be using weak acids and bases, generally speaking. Right? Weak acids are conjugate bases and stuff like that. So, for monoprotic versus polyprotic acids, just remember it's like phosphoric acid, right? So H3PO4, H3PO4, right? This is a polyprotic acid, right? Carbonic acid, H2CO3, also polyprotic. HCl is monoprotic, right? HCl, HBr, these are monoprotic, right? So monoprotic here, and then these are polyprotic, right? So, yep. Weak acids, conjugate bases. Just remember that there's many different types of weak acids and conjugate bases, right? Like I think an example would be like acetic acid, like we talked about, right? So vinegar, right? Generally speaking, I think in OChem we always talk about things that have like a pKa of 5. Like, we always talk about like those are the acids that you guys work with. So carboxylic acids generally have a pKa of around 5, and that's usually the most acidic thing I think you work with in OChem in terms of organic structures, if I remember right. So pKa we talked about, right? So the lower the pKa is, the more acidic the substance is. For pKb, lower pKb is more basic, right? And the other thing you can keep in mind is the Ka, right? So the Ka is separate from the pKa, but they are related, right? So the negative log of the Ka, or here, let's just do this actually. Negative log of Ka is equal to pK. I think I did that right. That seems weird though. I think that's correct. Oh, yeah, no, that should be correct, yeah. So another thing is that Ka is equal to 10 to the power of negative pKa. Right, that's the other thing you should know. So these two are related concepts, right? You should be able to solve for each of them. Apologies for my writing. It's not the best. Basically using a mouse and keyboard to type this out. Okay, so this is an important one. Titration midpoint versus equivalence point. Stoichiometric point. So the titration midpoint is the pKa. Plain and simple, it's just when the amount of base equals the amount of acid, and I'll show you that when we get to a titration curve. And the titration equivalence point is the point at which you get rid of all of the buffer, right? So the buffer is just gone. There's no more buffer anymore. And you need to add an equivalent, usually, of said substance, or of some sort of base or acid to actually get out of the buffer, usually. Okay, we're back. The recording died for whatever reason, so we're gonna have to do the slide again, but that's okay. So basically what I was saying about this slide is basically just showing you how we make these equilibrium equations, right? How acids dissociate, right? So if you look here, you got hydrochloric acid, right? This dissociates in a manner where it, HCl splits into H plus and Cl minus, right? And when we put it in water, like most biological systems are in, the only difference is now we have H3O plus and Cl minus as opposed to just H plus, right? For weak acids like acetic acid, right? Similar deal, right? If you just have this, right, turns into H plus and CH3, right? In water, it's same thing, right? H3O plus back here, right? So, yeah, this is described by the equilibrium constant, right? So Ka, right? And this is written as H plus A minus divided by HA, right? And that's the Ka. we also use this to figure out just equilibrium constants in general, not just Ka. So like when you see the equation negative RT, that's a horrible R, but ln KEQ, right? This is also an equilibrium constant, right? Just for a different reaction, usually not an acid-base reaction, right? So, God, my voice, Jesus Christ. Okay. Anyways, for acid dissociation constant, we're looking at this idea that a higher Ka means that this must be really high here, and this must be lower, right? Which means that we're getting a lot more of our dissociated product, right? Because remember that HA is H plus A minus, right? So if we have a lot of this top stuff here, it means that we have a lot of this and this, which means that this reaction is proceeding this way a lot more, right? If that makes sense. So that's what a high Ka means. That means high acidic strength. That makes sense, right? We just said that if there's a lot of this stuff, that means this is being dissociated a lot, right? And then a low pKa. And recall here, right, pKa is equal to the negative log of Ka. So it's a bit of an inverse relationship, right? If Ka is higher, pKa is lower, right? So just keep that in mind. And here we have different Kas, pKas. I honestly wouldn't memorize these. I would just say, like, the lower the pKa, the more acidic it is, the higher the Ka, the more acidic it is. And I would also keep in mind that you should be able to do these kinds of logarithmic conversions in your head, or like at least like approximate it, right? It doesn't have to be exact, right? So like for this one, for example, I can tell you that it's going to be probably between like 3 and 4, right? So if I take the negative log of 10 to the negative fourth, right, it's going to be like 4, right? And then if I take the negative log of like 5.6, it's going to be like 0.7-ish. And since negative is negative 0.7, so it's going to be about 3.2, 3.3, I had to guess, right? You can pick up some landmarks for this, right? So like, for example, the log of like of 3, for example, is 0.5, which is how I'm approximating this, right? So I'm just saying that, okay, this is above 3, it's around 6, right? So it's probably about 0.7 maybe, right? Something like that. So, and then I know my log of 10s, right? So the log of 10 to the fourth is just 4. So the log of 10 to the negative fourth is negative 4, right? So we can do things like that to sort of approximate this and make things faster. And I'll probably go over this in my lecture in person when we do this, for those of you who are watching this at the same time. And I guess I'll try and do a bit of a sample here. So like the way you would solve for this, right, is you would do the the log of, here, can I just like erase all of this here? Yeah. So the log of 5.6 times 10 to the negative fourth. This is basically the same thing as saying, actually negative log, right? The negative log of 5.6 plus negative log of 10 to the negative fourth. This is what this is basically saying, right? And then for this, if we solve this, right, like I said, negative log of 5.6 is like negative 0.7, right? So it'd be negative 0.7 plus negative log of 10 to the negative fourth. 10 to the negative fourth log of 10 to the negative fourth is just negative 4 times negative 1 is just 4. So 0.7 plus 4 is 3.3-ish, right? So it's around 3.3. That's probably what the answer is, right? Okay. This is a very big deal. This is very important, okay? Henderson-Hasselbalch. You probably remember from Gen Chem a little bit, right? It's nothing crazy, but what you should know about this, right, is that we have our Ka, right? And to take our Ka, we can use our Ka to basically calculate the pH if we're using a buffered system, right? So this is basically just showing you how we get to the Henderson-Hasselbalch equation. You don't need to derive this on your own, and you don't really need to know how it's derived, at least from my experience when I took the class, but I think it's helpful to know because it is literally taken from the original expression, right? So, I mean, basically what they're doing is that they're taking the negative log of both sides first, and we know that the negative log of Ka, right, this is pKa, right, if you remember from before, the negative log of H plus is just pH, right? And so then you're just going to be left with this simplification, right, leading into this simplification right here, right? So that's how we're basically coming up with this equation, right? And then obviously we're, in order to get this, all we're doing is just reorganizing it. We're adding log of A minus over A HA to both sides, right? So this is a very important equation. You can only use it for buffered systems though. So just keep that in mind. Okay, here's the titration curve. My throat is killing me. Okay, here's the titration curve. So for this titration curve, right, I talked about the midpoint, right, and the equivalence point, right, and you can see here that we have equivalence, right, on this x-axis here. So this is kind of leading into what this equivalent is, right? But yeah, so if we look at what's described here, right, titration curve of an aqueous solution of a weak acid or base, right, or this is a weak acid in this case. Well, how do we know it's a weak acid? Well, the pKa is relatively low, which suggests that it's most definitely a weak acid, right? The lower the pKa, the more likely it is to be a weak acid, right? If it's higher pKa, maybe it's more likely to be a weak base, right? So if we look at the steep ends, right? So these large changes in pH, right? That's when the buffer is broken, right? When the buffer is broken, we don't have the buffer's obviously not working, and so we get these massive changes in pH because you're just adding straight hydroxide, right? Or if you're adding HCl or straight like acid, then it's just going to drop the pH instead, right? But if you notice here in this region here, which is nicely labeled for us on this side, this is the buffering region, right? This is where the pH doesn't really change that much, right? So we go from 4.76 to like 5.76, right? Up here probably. And then to, I'd say around like 3.3-ish, somewhere maybe, more like around here probably is like, so like around there, right? So 3.76, right? So that's something you should know, right? These pKa's usually operate in a plus or minus 1 range, right? Maybe plus or minus 2, but usually not, usually plus or minus 1, right? Plus or minus 2 is a bit sketchy, right? So I would stick with plus or minus 1, and that's how I would kind of go with this personally. But yeah, and then these are the equivalents of OH added, right? So if you notice that if you add a bit of base, right, you turn some of this acid into base, right? And then you would increase your pH, right? But because you're in a buffered system, it doesn't actually change it by that much. So if we think about this in terms of Henderson-Hasselbalch, pH equals PAA plus the log, I'm just going to use base over acid, so B over A, base over acid, right? Or actually, no, we'll make it more consistent. So A minus over HA, right? This is what you guys are probably used to using. I use B over A just because it makes my life easier. But I did actually get docked points on an exam for doing that. So definitely keep that in mind. So for this, right, what we should note is that if we just have purely acid, right? So we start here, right, with zero equivalents of thing, right? We just have this CH3OOH, right? Let's just say that we have 1 mole, right? 1 mole of this acid, right? If we add 0.1 moles of hydroxide, right, you would deprotonate 0.1 moles of this acid, right? And then you would end up getting you'd have not 1 mole, but you now have 0.9 moles of the acid and 0.1 moles of the conjugate base, right? Because we just added 0.1 hydroxide, right? You can see that if we add 0.2, right, this would be 0.8, this would be 0.2. If you add 0.3, 0.7, 0.3. If you add 0.4, 0.6, 0.4. You see a pattern here, right? As we add more base, the amount of base, conjugate base goes up, but the amount of acid goes down, right? If we get to this point here at 0.5, you'll notice something interesting is we get 0.5 and 0.5. They're equal, right? If we plug 0.5 and 0.5 here, right, so we have 0.5 base, 0.5 acid. That just makes this whole term 1. The log of 1 is 0. pKa plus 0 is just pKa, so the pH is just equal to pKa, right? That's what is said here. That's how this works, right? That's how you get this term, right? And so that's how you go from, that's basically how you use the Henderson-Hasselbalch equation, right? You can basically substitute values in for the base and the acid, and you can calculate what the pH is, right? Given the concentration of these two, right? That is the use of this equation. Other than that, that's, I think, the main point I think I want to get across for this slide. So moving on to the next one. Yeah. So midpoint versus the equivalence point, right? This is where we're talking about like the pKa, right? So the pKa, right, is the midpoint. Plain and simple, for any given acid, right, the pKa is the midpoint. The equivalence point is the amount of base slash acid that you need to add to basically break the buffer at the other end, right? So for here, right, in order for us to break this buffer, we had to hit 1 mole, right, or 1 mole of hydroxide added, right? So that is the equivalence point. Right? The equivalence point would be here for this guy, right? And you can see here it says the moles of acid is equal to the moles of base, right? So that's the big idea that I want to get across for that. You can see here if we move down, we get to the concept of equivalence, right? And you can see here the equivalence is, one equivalent is equal to the total number of moles of acid plus base, right? So if you have 0.5 moles of acid and 0.5 moles of base, right? That means that one equivalent would be 1 mole of said acid base, right? So 1 mole of hydroxide, right? So if I had 0.5 acid, 0.5 base, add these together, one equivalent is 1 mole, right? And so if I add 1 mole of sodium hydroxide, right, I would take, if I started with 1 mole of just the acid, right, and I added 1 mole of sodium hydroxide, I would go all the way from this point here to this point here, right? Hopefully that makes sense, right? It's just this idea that it's basically relative, right? Because we want to know how many moles of our actual buffer are present in the solution, which is why we can't really use like a universal, or we can't really use like a specific measurement, if that makes sense, right? And like I said here, right, it's a constant for a given buffer, right? And the mole fraction tells you how many equivalents of a strong base have been added to reach a given pH and vice versa, right? So yeah, if you see here, right, if it tells you, if you look at this value here, 0.10 to 1.0, right, basically tells you how much base has been added, right, to reach the given pH that you're looking at, right? Okay, so if we look at the next slide here, right, we can see that, right, so if we have a buffer, right, and you add the acid, right, well, sorry, let's just start without a buffer. If you don't have a buffer, right, and you add an acid, right, the pH just drops down significantly, right? That's the point of the buffer, is to stop this from happening. Similarly, if you add a base, right, it's just going to destroy it completely. We go from pH 7 to pH 11.5 if you add a base, pH 7 to 3.2 if you add an acid. Buffers, right? If we look here, this is without the buffer, this is with the buffer. Oh, sorry, this is without buffer, this is with the buffer, right? 7.0 to 6.8. 7.0 here to 11.5, but 7.0 to 7.2 here, right? And I'll show you how this works in the lower slides, but that's the main point to get from this, is that buffers resist pH change. hammer home that point, right? Buffers resist pH change. How do buffers work? Yeah, so I'm not gonna lie, they took a lot of slides to explain this, so I'm just gonna try and pick out the slides that are important for you to know. This slide, keep it in mind, right? Know that water has this constant, 1.0 times 10 to the negative 14th. Basically, everything adds up to this number. So Kw, for example, is equal to Ka plus Kb, or times Kb, right? Keep this in mind. The whole idea where we use pKa plus pKb equals 14, that also comes from this idea Kw, right? Kw is negative 10 to the negative 14th, right? So just keep that number in mind, right, for the dissociation constant of water. But it doesn't really matter too much. Right? I don't think I ever really had to use this when I was in biochem, but you never know, right? How do buffers work? So yeah, so I mean, let's see. I feel like for this, right, it's the same idea, right? We're looking at these different compounds, right? Here's the Ka of that, here's the Ka of this. Notice the Ka of this is much higher, right? This is a higher number than this, so this is more acidic. Acetic acid is more acidic than water, right? Makes sense. We should know that, right? Like here, right? And here's how this works, right? So if you look at this, right, we have just pure water here, right? And you add this acid, right? It'll make the solution more acidic, right? I mean, that hopefully that makes sense, right? If you add an acid to a solution, right, we make it more acidic because we put more protons in the solution, basically, right? And so now we have a solution of this acid plus its conjugate base, right? Because once you put this acid in here, it'll dissociate to reach equilibrium within this solution, right? So now we have some amount of acetic acid and some amount of the base, the conjugate base, right? If we look at this, right? Again, repeating what I said here, right? That's all this slide is doing. This slide is just talking about how there is both the acid and the base form in here. Now, here's the interesting part, right? Let's see if there's a better slide for this. Slide is technically incorrect. I want to use this one here. Yeah, so this one here shows it very well, right? Let's say, right, that you add H+, right, to your solution, right? To this solution here, right, we add a bunch of H+. What's going to happen is the basic forms, right, will soak up the protons, right? And basically, you'll just get more of the protonated form of the compound you put in, right? But because acetic acid is a weak acid, the pH will not decrease by that much. Hopefully that makes sense, right? Because if we didn't have the acetic acid conjugate base in there, that H+ would be added and it would just sit there, or it would attack onto water and become a hydronium ion, right? And hydronium ions have a much higher hydronium ions have a much lower pKa, right? It's like -1, right? Which is why if you saturate, right, and you put too much H+ in, you hit the equivalence point, right? Because now you've gotten rid of, just imagine this is also protonated, right? If you add too much H+, right? Now everything is protonated and you just add more H+ in and it's just going to take up more space in here, right? And make this way more acidic than it actually is, right? So there's no more buffer if you do that, right? That's the point of the equivalence point, right? We're trying to figure out how much of this we can add before we break that buffer, right? Similarly, instead of adding H+, if we add OH- instead, now we can go the other way, right? We go this way, right? You add a strong base, what's going to happen is you're going to deprotonate all of these, right? And you see we have more minuses here, right? But because this is, again, a weak acid, weak base, it doesn't really matter if you deprotonate it, right? By deprotonating it, it doesn't really change the pH by that much. The alternative is that you deprotonate water, or you just put AOH- in here, right? And OH- is very basic, right? And so, like we said before, this is what happens in a buffer, right? If you reach the equivalence point, you've reached the point where you have deprotonated all of these H's on these acetic acids, right? And you are now just adding straight OH minus to your solution, which makes the solution far more basic, right? So adding straight OH minus here just makes the solution extremely basic, right? That is the idea of the equivalence point, and that's how buffers work, right? We're basically trying to saturate things. So if we're adding a buffer in there, or adding a compound that can soak up the protons or soak up the hydroxides so that they don't actually drastically affect the pH of our solution. This is just trying to say that there's many different buffers, right? So different compounds have different compounds just have different pKa's, which is why we're able to use, and basically you want to use, depending on the experiment you're doing, you want to use a compound that has a buffering pKa at closest to the compound you're trying to study. So if you're trying to study like human physiology or blood, you want to use like the bicarbonate buffer system, right? Because that's exactly what the blood uses, right? It's like around 6.1 pKa, if I remember correctly, something like that, right? So different buffers have different pKa's, so just keep that in mind. Right, and we talked about this, right? So just if HA equals A minus, so 0.5 and 0.5, remember we talked about this before, pH equals pKa because log of 1 is 0, right? If the HA, so the bottom, is greater than the top, right, the log of a number less than 1 is always negative, right? So pH will be less than pKa because you're taking pKa and subtracting it. You're subtracting some number from pKa, right? On the contrary, right, if you take the A minus, right, more base than acid, right, log of any number over 1 is going to be greater than 0, right, or greater than, it's going to be greater than 0. Yeah, it's going to be a positive number, right? And so pH will be equal to pKa because now you're adding a positive number to pH, right? This is a fun question that they like to ask all the time. Performing an experiment at that you would like to, at pH 8. So this is the big thing, right? So pH 8 is what we want this to be around, right? You have ammonium and phosphate buffer available, right? So they're basically saying that you're using either this buffer or this buffer. The experiment reaction generates H+. Okay, so it generates H+. So the solution is going to become more acidic, right? Which is the better buffering system. So this is really important here, right? Because if it said it was going to become more basic, you'd have to use a different train of thought, right? So let's go through the answer options, right? So we have the ammonium and we have the phosphate buffer system, right? We want something that's going to stick around pH 8, right? So let's think of, where's pH 8? pH 8 is here. So let me use a different color, actually. Let's use purple here. The pH 8 is here, right? Geez, okay, that's horrible. pH 8 is here, right? Not straight, but you get the idea. Okay, so pH 8 is here, and we're also using we're also producing H+, which means that we're going to drop down in pH as this reaction, whatever this reaction is, occurs, right? Because the reaction is producing H+, right? Which means that pH will decrease, right? So what that means is we want a buffer that is able to resist that change in adding more H+. If you look at the two curves, right? For the ammonium one, right? If we're adding H+, we're going to go down, right? There's quite a steep slope here, right? It looks like if we go down more, we're just going to go down to pH 7 like almost instantly, right? That's a bit of a problem, right? Because we're at this point in the buffer, right? For ammonium. Let's look at phosphate. For phosphate, we're at this point in the buffer, right? If we go down, how much does pH change? It doesn't change by that much, right? So based off of that logic, we can probably assume that we're going to be using the phosphate buffer here. Now, let me switch it up a little bit. What if instead of producing H+, this thing produced OH-? I'll let you think about that for a second. So, if it instead produced OH-, how would that change the answer? right? So now, okay, so let's think about it. Instead of, if it's OH minus being produced, right? Instead of going down in pH, we're going up in pH, right? So we need to go up in pH and see where the pH stops changing. So here's the buffering point there, here's the point there. If we add OH minus and increase the pH on this line here, you can see that we go from, I don't know, like pH 8 to like 10. Like basically the slope here is really large, right? But if we go from 8, start from 8 on the ammonium system, we go from like 8 to like not even up to 9 when we're adding like 0.1 equivalents. So in that case, you'd use the ammonium buffer, right? So this is what you have to be able to do when you're looking at buffers, right? You should be able to see that depending on whether or not the system produces H plus or OH minus, which one is better to use in different situations. Hopefully that makes some sense. Ooh. Yeah, so here's a classic example of a polyprotic acid. Phosphoric acid is one of like the most common buffers we use in scientific experiments, just because it has 3 different buffering ranges. So you can do a lot of experiments with this. Also, this is really close to physiological pH. Like blood pH is around 7.2. Although the pKa of bicarb and that stuff is around 6, if I remember correctly. So that's just what this is trying to say, though, that, you know, there's plenty of really cool compounds you can use for buffers, and phosphoric acid happens to be one of them that has 3 different pKas, right? Yeah, so here's what it says. Our buffering range is around 2 pH units plus or minus 1 of the pKa, right? So like I said before, I said you could do plus or minus 2, but I think for the sake of this class, right, do plus or minus 1. 2 is very sketchy. Usually it breaks. And yeah, the maximum buffering capacity is defined by the amount of acid and the amount of base, right? That makes sense, right? If you have more of it, the more you have to add in order to get rid of one or the other, right? Like if you have a beaker, right, and you have a lot of A minus in it, right, you'd have to add more H plus to turn it all into HA, right? Or if you have less of it, you require less of it, right? That seems to make sense, right? So, yep. Okay, so they always talk about this thing about dynamic, right? What the heck is dynamic? When we talk about dynamic, I think we're always talking about how things are just changing, right? So things are moving, things aren't they're never stagnant, right? So yeah, so within cells, right, the primary buffering system is the phosphate buffer system, right? And the pH of the cytoplasm around 7, right? Lo and behold, if you remember, where did it say? pH pK 7.2, right? So that's a great range, right? For that, right? Physiological blood pH, right? 7.4 phosphate could be in the blood, and I believe there actually is the phosphate buffering system in the blood. It's just not as important as the bicarb buffering system. But yeah, you look at this, large changes in blood are dangerous. Yep, this makes sense, right? Because all those proteins that you need, right, they need to be at a certain pH level, and 7.2 is optimum for a lot of them, right? So that's why it's important that the blood be maintained at a certain pH, which is how we, you know, the way we regulate pH is through respiration, right? So if you remember from Bio 220, you breathe in, right, and breathe out, right? You try to exhale the CO2, right? And the CO2 is part of that buffering system, right? And here is the equilibrium. This equilibrium, please remember it. Right, this is so helpful, and this actually showed up on my exam. There were 12 free points, just asking which way does the equilibrium go, based off of this, right? Here is the Holy Grail, the bicarb buffering system. So, the ones you really need to care about here are basically from here to here. You don't really need to care about this K3. It is there, just be aware of it. But this is basically how the buffering system works, right? And so the way that we actually end up getting the pK is a combination of K1 and K2, if I'm not mistaken. So that's pretty much what you should know for this. But yeah, so these two combine, right, to make water and carbonic acid, right? And then this dissociates into H plus, H3O plus, and bicarb, right? And this right here is the main, I would say, is like the main thing that buffers the blood. Usually this reaction here is not as like this dissociates relatively quickly because of carbonic anhydrase. It's an enzyme in the blood and in red blood cells. So yeah. Right, so here we said, right, CO2 is rapidly converted to bicarbonate, right, catalyzed by carbonic anhydrase, right, that's this whole reaction here, right, CO2 is exhaled in the lungs, right, yep, and so remember, let's think about this, right, if CO2 is exhaled in the lungs, the concentration of CO2 would decrease, which means that this would shift this way, and you would have a lower amount of H plus, so you'd actually end up with alkalosis, right? This is the kind of stuff that they will ask on your exam if you're given questions like this, right? So just be aware of that. Rate of respiration controlled by the brainstem. Yep, see, that's what we just talked about, right? If you increase the respiration rate, you decrease CO2, right? So this shifts to that side, right? If you hold your breath, on the other hand, right, you'd actually increase this, right? And you'd actually do this, right? And then you would end up increasing H plus, which is why you feel the need to, you're forced to start breathing again because you actually sense this buildup of H plus through chemoreceptors, right? So it's a really cool system. And here's what I was talking about, right? Where the way that we calculate the pK for this blood buffering system is through the combination of Ka and Kh, which is the conversion of CO to carbonic acid and then to bicarbonate and H plus, right? So here is that math, right? Take this and this. This is not really that important, to be honest with you. I've never had them ask a question on this. They'll ask you questions on like the actual blood buffering system itself, and like they might ask you to calculate like, oh, what's gonna happen to the pH if this, like if you add this much acid, right? In that case, you just use Henderson-Hasselbalch, and instead of for the pKa, right, you use this value, right? So like for pH equals pKa, right? pKa plus log of base over acid, right? And for base over acid, right, in that case, it would be here, right? This is what you want, so, right? So the log of HCO3, right? HCO3 and CO2, right? I don't know why I had to write that down because it's literally down there, but right. So you just use this, right? So whenever you're given a question about, oh, the blood has received a bunch of H plus, what happens to the buffering system, right? Use this, right? It's actually a bit interesting because it's using like the acid over the base, but it's a bit weird. But I wouldn't worry too much about that. This is one of those things where you could probably just memorize it, right? Now, if we move down here, right, so this is important. Under normal conditions, pH is maintained within plus or minus 0.5 units. Yeah, so it's very tightly regulated, right? So during exercise, if you have aerobic respiration, right, you produce a lot of CO2, right? And if you remember, right, if we produce a lot of CO2, we end up going this way, and we produce a lot of H plus, which decreases pH, because remember, they're inverse, right? The negative log of H plus concentration equals pH, right? So it's important to recognize, right? Under anaerobic respiration, the same deal, right? We produce lactic acid, right? Which also decreases the pH, right? So we always end up decreasing our pH. And that begs the question, why is the blood buffering system tuned with a pK of 6.1, not 7.4? Remember, what did we talk about? Way up when that ammonium and phosphate buffer system question, right? If we have just a graph like this, right? And we do this, right? If, right, we had the pKa at 7.4, that means that it'd be the midpoint, right? That means that you'd only have like half of this, right? Either side. The body is tuned in a way where almost all of the reactions in your body produce acid, not base. They don't produce a lot of base in the body. They do sometimes, but it's not that much. Like you saw up here, right? Anaerobic respiration produces H+, lowers the pH. Aerobic respiration produces H+, lowers the pH. Protein catabolism also produces H+ to an extent. All of these things produce hydrogen ions, right? They make the solution acidic, right? So there's really no need for this upper portion, but we do need a bigger safety net down here. And because the body produces so much acid, the danger is that because it produces so much acid, if you start at 7.4 and you produce a lot of acid, you actually might just break the buffer and you actually might just die. Because you'd go from 7.4 to like 3, and then all your proteins would denature, and then it would be horrible. But the cool thing is, by starting at the pKa of 6.1, we start out, we are already like quite acidic, right? So there's room for that buffer to basically buffer, right? So like, remember, so for pH 7.4 is where we're at, right? Let's just say that this marker is 7.4, right? And this is 6.1, right? We're now here, right, in our buffer. So if we add H+, you have all of this room to decrease the pH without causing any problems, right? That's what we talked about up here, right? Because we're producing H+, you want to be up here, right? Or in this case, it was up here, right? Not down here on the buffering system. That's why we use the pK of 6.1 instead of 7.2. Hopefully that makes sense. If you have questions, feel free to DM me, ask me. But yeah, hopefully that makes sense. And the last couple slides we're going to end off with are relatively simple. Right, so we should be able to explain all these, right? Some of them are a bit interesting, right? But like, you should be able to explain hyperventilation pretty easily. Prolonged exercise, you should be able to explain, right? You can probably explain this, right? Loss of HCl from the stomach. And apnea, possibly, right? Like the closage of like your airways, right? So you can't really breathe, if I remember correctly. So if we think about this, right? So CO2 plus H2O. Think about this, right? So hyperventilation, what does that mean? Decrease CO2, right? Bang. Decrease H+. Alkalosis, more basic. Perfect, that makes sense. For prolonged exercise, right? You would increase CO2, right? Because your cells are producing more CO2. Go this way, make it more acidic. Acidosis, perfect, makes sense, right? Extreme apnea, let's assume that it means closage of that airway, right? So you can't breathe, right? More CO2, right? This way, more H+, more acidic. Acidosis, that makes sense, right? Let's think about this. I haven't done this one yet. So prolonged vomiting, loss of HCl from stomach, right? So it leads to alkalosis. Well, how does that make sense? Well, for it to lead to alkalosis, that means that we would have to we'd have to drop this, which means that we'd have to go this way somehow. So you'd lose HCl from the stomach, which means you'd do that. So somehow this would have to happen, right? So you can basically see you can use this to get back to this, or you can use this here, or whatever, to get back to this effect here, right? They should always like complement each other, right? One leads to the other, and you should be able to work backwards from that, right? So this is just a summary, right? pH is important. Cool. Keep that in mind, right? It's going to be really important for future lectures, right? So get comfortable with Henderson-Hasselbalch. This is true. You need to be able to work with it, right? It's going to show up on your test, I guarantee you. No, it's not even funny. Like, it's guaranteed to show up on your test. I'll bet you money on it. Equilibria important, linked equilibria, right? And then making predictions for different solutions, right? So this is the idea of like if you add like H plus to that like ammonium solution or that phosphate solution, how does it change, right? So yeah. Here, right, we have some terms, right? Ka, strength of an acid, pKa, strength of an acid, right? Higher Ka, stronger acid, lower pKa, stronger acid. Midpoint, right, is when HA equals A minus, which means that the pKa is equal to the pH because of the Henderson-Hasselbalch equation, right? And then the equivalence point is when all of the weak acid has been neutralized, or all of the weak base has been neutralized, right? If you're using H plus here instead of H minus, and you're looking at a weak base, not an acid, right? It goes both ways. Bicarb buffer system, right? Buffered by the bicarbonate system, right? We turn CO2 into bicarb, right, and H plus through this reaction here, this set of reactions here, right? You increase H plus in the blood, right? Through exercise, right? You end up exhaling extra CO2, right? Write out that equilibrium, right? Get used to writing out that equilibrium of CO2 plus H2O makes bicarbonate H plus, right? Get used to figuring out what happens if you manipulate different sides of that equation, right? That will show up on your test most likely. And then here is that buffering system in all of its glory, right? Here's that pK, right? Here's that equation. Probably shows up on your test, right? In some shape or form, the blood buffering system will show up, right? So just keep that in mind. I hope this video was helpful. It was a bit longer than the last one. Anyway, I feel like it might have been a bit more rushed, so I apologize for that. But hopefully, at least it made a little bit of sense. And for those of you who are watching this at the time where I'm actually doing in-person lectures as well, or review sessions as well, if you have any questions, stop by and feel free to ask. Thanks. Bye-bye.